Hello, everyone. Hope you're enjoying the conference so far. In this session, we have a tutorial on using zero-cost proxies for neural architecture search going beyond CIFAR-10 by Gabby and Jovita. Jovita Lukasik is a postdoctoral researcher at University of Siegen, and Gabi Kadlecová is a PhD student at Charles University. So without further ado, I would hand over to Jovita and Gabi.
Great. Thank you very much, Rhea, for that nice introduction. So we will talk today a little bit about zero-cost proxies performance prediction beyond CIFAR-10, i.e. being NAS. Therefore, the outline, not working, but yeah, there we go. Okay, so the outline is going to be like a short introduction about NAS. We have seen that already on several different presentations, so that's going to be very quick. But then a little bit into the direction of what is performance prediction. We will talk about zero-cost proxies, the basics idea, and how can we move them beyond CIFAR-10. We will show you how to integrate them into the NAS process, how we would think would be a good evaluation of zero-cost proxies in general, and then we will show you some hands-on tutorials. Exactly. So as we all know, deep learning was kind of the main driver for the success in several machine learning areas with the goal of finding high-scoring efficient networks. And we also know the limitations of hand designing neural architectures. It's very time-consuming, it includes a lot of trial and error, and also involves this expert knowledge issue. And therefore, kind of the consequence was the idea to automate the overall architecture design process in terms of query efficiency, which led to the research area of neural architecture search. I think that should be already known for all of you. And also that we have already seen in that keynote from Aaron today. But just again, here we have an overview of neural architecture search with the three different components: the search space, the search strategy, and the performance estimation strategy. And to put everybody on the same page here, we will start to give you a short overview of what kind of different search spaces are available actually in the research. So mostly cell-based search spaces are the common search spaces used in neural architecture search, where each architecture is represented as a directed acyclic graph. So it's mostly inspired by the idea of human-designed convolution neural networks, for example, the ResNets blocks, where the ResNets blocks are just repeatedly added into an overall architecture. And that's how it started actually with the first search space called NASNet, where the search was to search for small cells and then stack them several times. Therefore, we search for the so-called microstructure and have a fixed macro architecture. So therefore, we just search for the small cells here. There are different types of cells depending on how you actually define a search space. Either just a normal cell. Oh, we don't like that. Either just a normal cell or a reduction cell. So just to put you all on the same page. And of course, there are like several benchmarks available. NASBench101, for example, was kind of the first search space, also kind of given us by Aaron. That was very helpful, just as an idea, as an information. There we have all the information on the nodes. And NASBench201, we have all the information of what we want to search for are on the edges. But I think that is something which most of us should already know. The interesting part is also the so-called TransNASBench101 search space, which does not only look for the micro search space, but also for the macro search space. So we search for either the cell or the overall architecture of how, on what kind of points do we want to downsample and what kind of channels do we want to have. All these search spaces differ also on what kind of training data they use, the amount of search, the amount of architectures, and what kind of operations we have. But of course, there are also like more simple basic variants, which are quite important nowadays, which are the so-called chain structured search spaces, where it's actually just like that we want to have a chain structure of architecture. So we build them repeatedly up one layer after the other, and it gives us more degrees of freedom because we can easily include any kind of multi-branches and make them wider, bigger, just include another kind of skip connections as well. These search spaces are rather important because they are also used in currently benchmarks, for example, the hardware GPT benchmark from Rhea, with actually kind of the idea to search for transformers. So these chain structured search spaces can be easily used with a transformer kind of structure where you want to kind of layer after layer search for different kinds of blocks, be it the embedding layer, the transformer block, or the prediction head, which is happening here. And as you can see, Also, the sizes of the search spaces differ. In that case, it's 10 to the power of 36. But that's just like to put everybody on the same page when we talk about search spaces and that there are several different kinds of search spaces. The good part and the actual part we are interested in is the performance estimation strategy. So we all know that predominant NAS methods are expensive. As Aaron also already said, the first paper used reinforcement learning, trained up to 20,000 different architecture, used 800 GPUs for 2 weeks. We don't like that, we don't want that. And therefore, so-called speed-up techniques were kind of evaluated and resulted to improve the query search and thus also to not have the need to train up to 20,000 architectures. Because in general, one query implies a full training of the architecture. And therefore, we want to use performance prediction methods. And that's what we will talk about today in the tutorial. So we will see a very nice short definition of what a performance prediction is. The interesting part is actually that we want to have a performance prediction method, which is, for example, fhat, which is a function which predicts the accuracy or any relative accuracy or any kind of objective or target you're interested in for the architecture and does not train it. So it just predicts that kind of metric you're interested in. And the idea is that it just takes less time than evaluating the actual metric on the actual data in the training pipeline of that architecture. And ideally, this predicted metric has a high correlation or rank correlation with the actual metric on that architecture. So we have seen also already this method. One of those are one-shot methods, which we also already seen in Aaron's talk or also on Monday from Martin, and surrogate-based methods. So I will just skip the one-shot method task. I think we all know what kind of the ideas. We have the super network, we extract the subnetworks, and we extract the inherited weights by it, and therefore can evaluate each subnetwork in it. The surrogate-based methods have the idea of exactly being the performance prediction method. We predict the performance of an architecture and don't train them fully, and these can be wrapped in different disguises. So we also have some pros and cons. The pros for the one-shot methods are that you only need to train this one-shot method once. It's a fast evaluation for each subnetwork, and it's advantageous because subnetworks are actually expensive to train, so you just can inherit the weights of the actual trained supernetwork. But the cons are the subnetwork's performance are often inaccurate given the inherited weights from the supernetwork. The overall supernetwork architecture is fixed, so that needs to be predefined in your actual search space. And the performance estimate still requires the evaluation on the whole data loader. On the other hand, we have the surrogate-based methods. They are easy to train. They're combinable with tabular benchmarks, for example. There's a very fast estimation, and you can easily integrate them with different kinds of search methods. However, they can be quite inefficient because you still need some architectures, more or less hundreds of architectures, which are actually trained and evaluated to train the performance prediction method. So to just visualize what I actually talk about when I say performance prediction methods, we have 3 different components. We have the data. In this case, it's the architecture from a search space and the metric of interest f of a, given the amount of architectures you have in your search space I to n. You have an encoding, architecture encoding, and then you include that encoding as an input to the predictor method. And that predictor method has the target, of course, to predict the actual target you're interested in. The good part is that for the data set, it does not have to be the complete trained accuracy. You can also use it and combine it with, for example, learning curve extrapolation. And the architecture encoding is kind of something we will talk about today, also more about. So the performance prediction method, as I said, we have the data on the one side, we have the prediction method on the other side. And the prediction method, it's also something you can play around with. You can use GNNs, what we have also seen at a lot of talks. You can use a simple random forest method, XGBoost, LMP, whatever you like for a regression task. But the architecture encoding is kind of the gist. So you have actually, if we look at the search spaces, the cell-based search spaces, for example, you have always a directed acyclic graph. So the obvious idea is to represent the directed acyclic graph as an adjacency matrix and just flatten it and then use it as an input to the, for example, an MLP. But you can also use any kind of information like a path-based encoding, which eventually led to the paper Bananas by Colin, which also used different kinds of performance prediction methods. And also very interesting is that you can combine the performance prediction method with a search space, resulting in a surrogate search space. And the first surrogate search space, or the surrogate benchmark actually released in the NAS area, was the NAS Bench 301 search space, where we're also very happy to have Arbor here as a first offer. So instead of training each architecture in that Dart search space, which has 10 to the power of 18 different architecture, we use a surrogate to predict the accuracies of the architectures which were not evaluated. And actually, these surrogate methods were trained on and evaluated on 60,000 different architectures. So the 60,000 were actually trained and evaluated, and the surrogate methods, be it a GNN or an MLP, was it an MLP? An XGBoost, I think. GNN and XGBoost are actually surrogate models which were used to predict all the other architectures in this 10 to the power of 18 dimensional search space. So we know the goal in NAS is to find an architecture in an efficient way with the highest validation accuracy, for example, on the downstream task. And we want to use performance prediction method to improve on the search. We can use predictor guided evolution to combine the prediction method with regularized evolution, for example, or we can also use Bayesian optimization with prediction method, which eventually that you can just have an ensemble which calculates the mean and the uncertainty for the candidate architectures. But there was now a lot of technical information. To give you a recap, we want to have NAS methods, speed up techniques using performance prediction methods. And as an info, again, this performance prediction methods based on 3 different components: the dataset, the prediction method, and the architecture encoding. And the goal is to predict the performance of the architecture and not training them fully. However, as I also said, as a con, they require non-trivial computation time. And that's where the fun part comes in. So can we make this process any faster? What happens if we want to work with larger data set, new data set we have not explored before? Do we really want to train again hundreds of architectures? No, we want to use the so-called zero-cost proxies. And that's what we will talk about today. A zero-cost proxy has the idea. So we have a data set, for example, CIFAR-10, which we can see here. And we have the search space, for example, the NAS Bench 201 search space, which we also have already seen. And we calculate a score, for example, the number of parameters of each architecture. And we eventually hope that the zero-cost proxy score, for example, on the x-axis, is correlated with the actual accuracy of the architecture on the dataset you're interested in, here, CIFAR-10, that you have some correlation. And as we can see here on that part, if we have kind of a positive score, we can say if the positive correlation, we can say if we have a high score, we also have a high accuracy. Isn't that great? Because the score is calculated on the untrained network. And just to give you also some definition, what I actually talk about. Zero-cost proxies are kind of the estimation of the performance of an architecture, which is mostly based on computation from a single forward and backward pass of a single mini batch of data, meaning the most the architecture actually sees is up to 32 training data points, 1 forward and 1 single backward pass. Therefore, we omit the expensive training and evaluation of architectures. We have a score without the need to train the architecture. It's a fast computation. But again, it relies on the assumption to be correlated with the architecture performance on the downstream task. So, but to give you some idea, what are zero-cost proxies actually? For example, we can now use the L2 norm. The L2 norm is just the sum of the L2 norm of the untrained network weights. And we can see here on the example of NAS Bench 201, having the validation accuracy on the x-axis and the score, the zero-cost proxy score on the y-axis. So the higher the L2 norm is, the larger is also the validation accuracy. But what we can also see here is some colors based on color coding based on the number of convolution, but that will Gabi is going to talk about more, just to give you some hint that's going to be quite interesting. So what we can actually see is that there is some correlation, and you can say if you have a network with a high L2 norm, then it's probably also having a very high accuracy. In general, in the literature, there exists already a wide range of zero-cost proxies, for example, in NAS Bench 0. In this NAS bench, we have in total 13 different zero-cost proxies, which can be differentiated in different types. So for example, Jacobian-based zero-cross proxies look at the Jacobian information. We have pruning-based zero-cross proxies, which look at the pruning idea. Baseline methods, for example, the number of parameter, and also piecewise linear zero-cross proxy. So just as I said, Jacobian-based, for example, measure the covariance of the Jacobian matrices across one mini batch of data. The pruning-based ones can approximate the change in the loss, and baselines blobs and parameters. The more parameters, the higher actually accuracy in most search spaces. And just to give you a very nice image done by Arjun actually. So there are several different tasks on the x-axis on different search spaces and the 13 zero-cross proxies on the y-axis. And what you can actually see is that the darker the color, the higher the accuracy at the correlation, or the more yellow the color, also the higher the accuracy. And what we can actually see that there are some zero-cross proxies which have a quite high correlation, which already shows us quite a good idea of that we can use them somehow in the area of neural architecture search, because we have actually the correlation we are all interested in. The pros for actually using the zero-cross proxies is that they are easily and very fast to evaluate. As I said, only one forward and backward pass. They have a relative high correlation, and they are applicable at different NAS stages, which we will discuss later in this talk. But there are also negatives. It's not that there is one single best proxy across different search spaces, as we have seen also at the previous slide. It's biased by the number of operation and other network properties, and there's no explainability at all actually happening there. And what's new since NAS Bench Suite 0 is going to be presented by Gabi.
Okay, so this was like a really nice introduction of the basics. And so we had NAS Bench Suite 0, already quite a nice overview, quite a nice comparison. And now we can ask what has happened since then, what are the new proxies? So one part is, so far we were very positive about those zero-cross proxies, but then in the hands-on, you can actually see that there are also some negative. So mainly that some of the proxies are basically the number of convolutions on NB201. So that's graphed. It's like using different operation counts as proxies, or maybe path lengths. But apart from that, there were also some new proxies like Miko. But here we already see a flow in evaluation. So you just use MB201 and CIFAR-10, maybe ImageNet because it's easy. But then the proxy is not that good on the other tasks. So TransNAS bench here is really good because you've also got those autoencoder tasks, or some scene classification, not just CIFAR-10. So it's really good if people compare as well there. And so later, some Zico, SwapNAS, there were some new proxies with good results. Some of them are theory-based, but it's more or less, there's always something new, but it could be better. It could be better compared across different tasks. Those proxies that are listed here show some improvements, but later I will also show you where we can also get better in the evaluation. What would also be good if the proxies improved with training. So there's a really nice blog post by Colin White, I think, which showed that most of the proxies, when you train the network and then evaluate the zero-cross proxy, the performance the correlation just drops. But we maybe, if we would have some multi-fidelity setting, we would really benefit from proxies that improve with training. So one of them was LGA that improved a little bit with the training. You've got also some estimate, you get some early stopping validation accuracy or sum of training clauses until a specific epoch. So that is something that you can use and can be really nice. But if you would like to do work on zero-cross proxies, this is one way where you could maybe do something. Something also promising would be like evolving or designing the zero-cost proxies, because usually it's just like some clever people thinking of some clever theory, talking about NTK, then having some long proofs, but that's maybe not that approachable for like first-year PhD students, for example. So something like automatically designing the zero-cost proxies could be quite fun. And there's also some work in combining zero-cost proxies into new ones. So you take, for example, 3 zero-cost proxies and somehow average their score to have a new, better proxy. But there's always a question, like which proxies, what the weight should be, like is it a weighted sum or is it a ratio? But yeah, it's also a possible research direction. So the first, to wrap up, like the first survey kind of evaluated what we already have, but that's just like the beginning. You could think of so much more. So I will briefly give the word again to Jovita, and I'll be back soon.
Thank you. Okay, so we have a small introduction. We had a small introduction to zero-cost proxies. So we know zero-cost proxies are widely used and currently research method, and also how we can use them and what kind of disguise. We've also seen at several posters here today at the poster session. So therefore, they allow us to evaluate the performance of an architecture at almost zero cost. Yes, this pun is intended. So we don't have any architecture training. It's a wide range and they are easily adaptable into different NAS methods. And now we want to ask you, are there any questions so far for that introduction to the baselines and zero-cost proxies? Because we need to be here all on the same page for the hands-on. Okay. Are you sure? Oh, okay. Okay, then let's go beyond CIFAR-10 as the only single accuracy objective. So far, we know, for example, on vision task, what the people are interested in is in the accuracy of the architecture as a single objective. But we think the goal should be to go beyond single objectives, which we have also seen today at Aaron's talk. Hardware-aware objectives, for example, could be combined in a multi-objective manner. And that's what we will talk about also today, going beyond the typical benchmarks, which just provides us with information about the accuracy, for example, looking at hardware efficiency, having different hardware types available. And there is a lot of research already done with also new benchmarks, also new search spaces coming up. For example, the hardware awareness bench was kind of the first benchmark which actually introduced the importance of different hardwares. So on hardware awareness bench, for example, all the architectures in NAS bench 201 were re-evaluated on up to 5 different hardwares. So therefore, you could actually try to search for architectures with a certain amount of energy or latency on different hardwares. But as we have also seen on the keynote just before that tutorial, another important thing is, for example, the robustness of an architecture. So for example, we have here an image of a panda, and an architecture says it has a confidence of 58%, but it predicts it's a panda. But as soon as we add very little noise, we can see under C, it's a panda. And we as humans say, of course, it's a panda. What else should it be? But well, the network is to 99.3% sure that it's a gibbon. So I think that's actually kind of disturbing to know that these networks can be easily fooled. And there's also a lot of research done also in the area of introducing more robust architectures in general as and more robust accuracy as an additional objective into the area of neural architecture search. For example, there is the robustness data set presented last year at iClear, where we evaluated all unique architectures in NAS bench 201 against 3 different attacks, FGSM, PTD, APG, DN square, for different kinds of an amount of perturbation. So here on the x-axis, we can see 8 or 255 is already a very large perturbation added onto the image. And we wanted to see how well can actually the accuracy without any kind of difference in training kind of, or how easily can they be fooled? And we can see that the accuracy has a very large drop. So still also, if you design neural architectures or also search spaces, you can see that they are not at all robust. So that there's a lot of research still needed. And yeah, we will switch again.
Okay, so now it were like the tools. What can you play with? What are the available zero-cost proxies? What are the search spaces? What are the metrics? And now we'll go to how can you actually use zero-cost proxies or performance predictors to solve your diverse tasks, where you can, how you can use it for your search space, for NAS search, and maybe what's like the future where you can contribute in your research. So the first part is in the diverse metrics is the hardware error metrics that we saw at the keynote by Aaron, and also previously on, was it on Monday? Yes, was on Monday. So actually for the hardware error tasks, the zero-cost proxies themselves are not that useful because of how fast to evaluate there are. So usually you will just use a hardware predictor. So you will have the encoding of the network and you want to predict the latency or the energy. Like in some of the works, people have used flops and params to directly approximate the latency or energy. But I think that for, especially for energy, it was just a really rough approximation, and it's not really worth it because how fast you can evaluate that. Where it is interesting, and I think we already heard that, is to predict for the new devices, because there you want as few evaluations as possible. So that was like in context learning estimation of the hardware metrics. That's what you're aiming for, so that the prediction for the new devices is easy, so that you can deploy faster on the devices. But where the proxies can be used, or the predictors, is to make the evaluation of the subnetworks into SuperNet faster. Because for the evaluation of the subnetwork, you have to still do a pass over the validation data set. And for the hardware error measurement, you still have to measure it somehow. And if you just have a predictor that you can query and get the prediction directly, that can already speed up things. There are some examples in works. So for example, there was hardware transformers, once for all on NAS. These used mainly the one-hot encoding. Then you've got like BRP NAS, that's a graph neural network-based predictor. And also there are some predictors that use directly zero-cost proxies. So you can instead, I will talk on that later, you can instead collect all your zero-cost proxies and use them at the network encoding. And that's what multipredict and graph do. I'll talk about that later in the usage in NAS part. Second are the robustness error proxies. And this is like, if you are bored and want to do research in zero-cost proxies and don't know what to do, then there are not many zero-cost proxies for robustness. So you can come up with something clever or try to, like, I don't know, combine existing proxies to really handle the robustness tasks. Because there's like one proxy for robustness that uses Jacobian, Hessian. Also, Crozy is, I think, the only zero-cost proxy specifically tailored for robustness. I think it's got pretty good results. And also, what Jovita did is that she used several zero-cost proxies again as an encoding for performance prediction of the robustness tasks. So you can also check that out. All right, now the interesting part, because we've seen a lot of convolutional search spaces, but what else? Again, this is something where you or researchers can shine because it's rather understudied. Usually when you've got those L2 norms and gradient norms and number of parameters, that's pretty easy to adapt for your search space. It's maybe a bit adjustment in the code, but usually you can just directly obtain the scores. Of course, some proxies are limited by design. For example, NASWOT, which is kind of a good proxy, is limited to ReLUs, which you don't use in transformer search spaces. But there's not just transformer search spaces. There's not that convolutional search spaces. What I've seen as application, I've seen like a application of zero-cross proxies with pretty good results for GNS, for 3D point cloud processing, something also for human action recognition, and then some zero-cross proxies for RNNs. In general, there's plenty of space here. And actually, the proxies, especially in the 3D point cloud processing, I think the results were really good. So if you've got an applied problem, maybe just using some of the proxies can really help, because it helps you eliminate the bad networks. Because even though the correlation isn't perfect, you can usually just filter out those networks that aren't really worth it to evaluate. Transformers. So I've seen zero-cross proxies adaptable to transformers. There are also specific proxies designed for vision transformers, but research-wise, it's a bummer because zero-cross proxies are less important. So first, you've got Sakai link loss, so you can usually just approximate the perplexity. For example, decode the parameter count was a great proxy for that. And also the focus is a bit different. So for convolutional spaces, you trained all the networks, and you could train 100 networks or so. So here you're happy if you can actually train the one model. So the method of choice is just one-shot and ask, because it's just more convenient. But as I said, not all hope is lost for performance prediction researchers. You can train a performance predictor to like estimate the like validation or test performance at inference when you've got already the subnet weights. You can just speed it up. It's also multi-objective. So having the hardware ever predictors, that's something that you want to do here. But again, even so, for example, when Alpha or HAT use the predictor, that was still a one-hot encoding. You can't really use any fancy predictors because it's not a directed cyclic graph anymore, but there's a potential for improvement in here, just designing better predictors so you can just, for example, predict the hardware metrics more accurate. So we learned that hardware-aware predictors are just more important than hardware-aware proxies, that robustness proxies are actually a good idea, and that, I mean, there's not that much space for zero-cross proxies in the transformer search space, yet there are still some interesting places to go. Okay, now zero-cross proxies in the NAS process, where you can actually use them. Oh, questions. Are there any questions?
Do we have any questions?
No.
I might have one.
Okay.
As we also saw in the talk today morning, latency collection can often be very noisy. So it's very important to also model the uncertainty in latencies in addition to like just predicting it. And like, do you think proxies could be used for uncertainty or to quantify the uncertainty in latencies too?
Mm-hmm.
And that's, I think, one part. And the second one is latency collection, though like getting a single latency observation is cheaper, but if you want to then model the uncertainties, you often collect bunch of them, so that becomes expensive.
Yeah. I think it's like a good fit. Maybe not the proxies themselves as scores, but more like the encoding part, because that's what I will talk about now. Just using all of the proxies that you have leads to like quite a good performance prediction compared to the one-hot one. And since it's just a bunch of scores, you can really have a tabular data set, and then that combines well, for example, with maybe some Gaussian processes methods or like some other predictors that will enable you to quantify the uncertainty. And yes, especially if you have the noisy latency measurements, then that's something that you perhaps want to use. It's important also to see that it's not just the zero-cost proxies. You can, for example, use both the zero-cost proxies and the one-hot encoding, and maybe then the graph features to get even like better predictions.
Okay, thank you.
Okay, back.
Have any other questions?
Doesn't seem to. Okay, so how can we use zero-cost proxies? Because it's those weird scores, but as you will see, it's actually something that you can use. So just using it instead of validation accuracy is really simple, but maybe sometimes since the correlation is not that large, it might be that useful for you. You will see that in the evaluation section at the end. What I think is one of the best application is, as I said, collecting them for encodings of the architectures. There are also some places where you can include them directly in search, like in BIO for the surrogates, for warm static evolutionary algorithms, and also for pruning. But another interesting part is how you can improve like the GNA-based predictors. So the GNNs usually, when you have just them, they are not that accurate. So including the zero-cost proxies in there actually makes the prediction better. All right. These slides will be more like a quick overview. If you want to use some of those methods or read up on some related work, you can just look into the presentation that we will later share. But basically for encodings, the main idea is to get the zero-cost proxies and create like a tabular data set out of them. You will see that in the hands-on. There's a lot of work on that. So it was used for robustness prediction. It was also in NAS-bench with zero as using XGBoost, you predicted the accuracy of the rest of the search space when you sample just a few of them. Again, it's going to be in the hands-on a bit. So it's no longer zero cost. It's standard performance prediction, but it's better than using the one-hot encoding in most cases. So it's something that you perhaps want to do. Okay. Also, a nice property is that you can transfer across search spaces in theory, because before the one-hot encoding from NAS-bench 201 is really different than the NAS encoding of Dart. So the transfer wasn't really possible. But if you've got just 13 scores, you can theoretically try to transfer from NAS-bench 201 to Dart. Okay, the second possible application. So when it was used in evolutionary algorithms, it's usually you take the score, you score all the networks in the search space if possible, or like a lot of networks. Just take the networks with the best score, and that's like your initial generation. So here you hope that you will filter out those really, really bad networks and not like hinder your research. Yeah, this is more like if you're interested in it, read up on that. There's a lot of details. Maybe the last one, the operation scoring in super network. So people were using that for structural pruning, actually, of, for example, of the supernets, because you can use the zero-cost proxy to estimate if you should keep this operation or if you should remove this operation. It's also very interesting. So it would be maybe interesting to use it, for example, in those transformer search spaces. On the other hand, me personally, I'm a bit skeptical because it's kind of hard to evaluate. Like, is this zero-cost proxy better than a different proxy? Like, does it really indicate that this operation should be removed? It's like purely empirical. So you use one proxy, do a lot of pruning, and then you get some accuracy, use another proxy, do a lot of pruning, get another accuracy. But yeah, that's just personal skepticism. When there was like a poster on few-shot NAS where they use zero-cost proxies to decide which operations to keep, that one seemed to have quite good results. So it's one potential interesting research direction. Okay, the case of GNNs. So when we had the paper on the graph features that you will see in the hands-on and zero-cost proxies, so we use this as an encoding. We trained just a random forest, and we've got the results of the performance predictor. And this was better than the GNNs. That shouldn't be like that. The GNNs are learnable models that should just learn everything about the graph and just learn how the accuracy corresponds to the directed acyclic graph connections. Yet standard GNNs were just worse than a simple tabular predictor. But I don't think that the GNNs themselves are bad. So for example, one GNN called TA-Gaze that also includes the zero-cost proxies was, I think, performing on par with what we had. And also BRPNAS, another GNN predictor. When we added the zero-cost proxies and the features to it, the results got really better. I mean, right now, if we have the transformers, the GNNs are not that used there because it's more like you have the one-hot encodings. But if you've got like an applied task and still use CNNs or maybe something even something else, and still have those GNNs predictors, then what I would suggest is to just use one of the tabular ones or one of those that combine the proxies with the GNN itself. And it would be a really interesting research direction to just choose better GNNs for performance prediction, because it's just standard graph convolutional networks. And I will always like to say that, well, I found a paper if can graph convolutional networks count substructures? Well, the answer is no, if it's the title of the paper. And the case is that standard GNNs theoretically cannot, for example, count skip connections, because they can only count star-like structures, but not triangles. So if we want to use GNNs in NAS, we need better GNNs, because counting skip connections is quite like important in performance prediction. So yeah, that's more like a pet peeve, but couldn't help it. Right. So recap, zero-cost proxies are quite easy to include in your NAS search process, as you will see. And you get faster performance estimation than if you would use GNNs or some complicated method. The challenges are that they're not that interpretable, but GNNs aren't either, and that they don't improve with architecture training. So there's not that much flexibility. What would also be really interesting is to see how to choose the best zero-cost proxy for a new data set and a new search space. So some meta-learning perspective. It's hard to do because there's not that many search spaces and maybe data sets. But then if you could just get a good score to approximate something, the performance of your new task, that would really bump the usefulness up. Evaluation. So if you delve into zero-cost proxy research, you will mostly see that you look at permanent rank correlation of the network accuracy and zero-cost proxy score pairs. But as you will see now, there are some issues with that. So this one is more like if you have a zero-cost proxy and want to see if it's actually better than the other proxies, this is what you should ideally do. So if you consider SymFlow, which is one of the rather better proxies, you can see that the overall correlation is quite high. It's, I don't remember the exact numbers, but you can easily filter out those bad networks. On the other hand, on the right, if you zoom into the top few percents, like the best scores should be the best performing networks, you see there's like no correlation. So if you use it to warm start your algorithm and just get the top scored networks, you are back to step 0, because this is just like you have completely uninformed search because the zero cost proxy doesn't help you with anything. So what I think researchers should do when introducing a new proxy, or when you would choose a proxy for a problem, is that when you score a lot of networks, like all of the networks in NASBench 201, you would ideally look at what the best network performance in the top few percent of network score is. Because if it's low, it means like there's also a lot of noise. You didn't really filter out those bad networks. You are maybe also interested in what the score of the networks that were left behind. So did you discard actually the top 100 networks? Because that's not what you want to do. Yeah, and ideally you should also use a lot of other metrics. But if you can afford to evaluate only a few networks, then you can also look at what's the correlation of the top networks. Because if you can only evaluate about 3 networks, so if you would do that here and sample the network on the left, on the right picture, so like some really bad network, that's not really useful. So just to emphasize, this was something that's rather missing in the research of zero-cost proxies. There were some works that included some of other metrics and so, but still. The not that typical case is when you score only few networks, because zero-cost proxy evaluation is not exactly zero-cost proxies. Sometimes it takes several seconds at least, maybe even minutes. So, no, it was seconds, I think. No, I'm bad at remembering exact numbers, sorry. So usually it's fast, so you can usually score a lot of networks. But if you would, for any reason, not have access to the networks, then the Kadlecová and Spearman correlation is good. So the current evaluation metric that is used is not suitable for the typical case. So if you want to use zero-cost proxies, maybe take some of the other metrics, score the existing zero-cost proxies, which you can easily do using NASBench Suite 0, and then choose what suits you best. Oh, and if you someday introduce a new proxy, then report multiple metrics, please. As I will also show in the hands-on, so there's no interpretability, but that doesn't mean that you, as a researcher, can do an analysis. So it's interesting to look at the scatter plots, look at what the networks in the clusters are, look at the number of operations. It's actually quite fun. You will see that in the hands-on. But yeah, people didn't do that. They did do the scatter plots, but then the cluster examination or the number of operations wasn't done, as far as I know. Oh yeah, and evaluate on multiple task and search spaces. This is something that we discussed throughout the conference. So tasks beyond CIFAR-10 are interesting. One, there are tasks where it's still the convolutions, still the directed acyclic graphs, and not, for example, vision transformers. So if you have a non-traditional task, or if you include a new zero-cost proxy, just showing that it works for these tasks may be very interesting. And this is where I think the research should go of zero-cost proxies, like just really looking at on some search spaces beyond NASBench 201. So we, for example, the large search spaces like iSpace would be interesting. Also some, I don't know, yeah. And for the data sets, there's like plenty of, you've got, for example, 1D convolutions, you've got 3D convolutions. So lots of things where you could do that. All right, are there any questions before moving close to the hands-on? Or ideas, objections?
Hello. I was wondering, so do we know if zero-cost proxies are robust to things like the initialization of weights, if they depend directly on weights, just by like random seeds or potentially different initialization schemes? Does that have a big effect on these?
Yeah, as far as I know, yes. I don't know which of those works that was, if that was zero-cost proxies for lightweight NAS or maybe NASWAT, but at least one of them like did an analysis and it was really robust to the initializations. But it's possible that, so yeah, that was MB201. So it's possible that if it were some other task or other search space, it would not really be the case. But usually you can be quite confident that that it works. And some of the proxies aren't, I think, that affected. For example, if you have got a gradient norm, then maybe that wouldn't be affected, or the number of parameters, but this is not like a proper proxy anyway.
Yeah. A second thing, because we know certain proxies will be specifically good on like CIFAR-10 or very specific data sets. Do we know of other more weirder data sets where some work really well and can we therefore kind of quantify there's a difference between these tasks based on what kind of proxies are the best at predicting things?
Yes, I don't think we know that, and it's a really interesting research direction. So what we can say, I don't want to go too much back, but when you had the table from NAS-bench Suite 0 with all the correlation, what we know is that most proxies are good at image classification. That is something that we expect. The weird thing is that most proxies have trouble with NAS-bench 301, so DARTs, or NAS-bench 101. Some of those newer proxies, like the Miko or Zico, I think, had quite a large correlation, at least on those search spaces. But I don't think we really know why. And one of the reasons is that the zero-cost proxies, apart from NAS-bench, haven't been evaluated on so many tasks. So I think it would be really interesting to just try to collect more tasks and evaluate that. And that would then lead to the meta-learning ideas. Yeah.
Thank you.
Do we have any other questions?
Cool, then let's move on. So this is our recent work, and it's partially a criticism of zero-cost proxies, but it's also like some new zero-cost proxies. And to be fair, the criticism doesn't apply to all search spaces. So it's another reason why we should also look at something beyond NAS-bench 201. So the thing is, which you will see in the hands-on, some of the zero-cost proxies behave just like properties of the graph, namely the number of convolutions. On NAS-bench 201, two of them are like the same as the number of convolutions. People have not realized this, which means we should really analyze the zero-cost proxies better. But now the positive part is, why don't we just use the graph properties as proxies or as an encoding? And this is an amazing picture by Jovita, and it showcases some of the proxies. So on the top, you've got the standard NAS-bench 201 cell, and then there are 3 examples of the graph features. So on the left, it's the node degree if you count only skip connections and 3x3 convolutions. So in this case, it's 2. Then you've got the maximum path length. So the maximum number of operations you can take from the input to the output when you restrict yourself only to the skip connections. So if it's only the skip connection, the maximum is 1. But once you allow skip connection and convolution 3x3, it becomes 3. And the neat part is that if you collect these features like operation counts, node degrees, maximum path lengths, minimum path lengths, it's actually state of the art. So when you've got the zero-cost proxies, the graph features, put that into XGBoost or random forest, and you beat all of these predictors on from the survey, how powerful are performance predictors. It's graph neural networks, it's some XGBoost on one-hot encodings, there's also bananas, bonus, just everything that I could like get from the survey. It's a really simple encoding. And it's like, just zero-cost proxies are not sufficient. So you have to really include the path lengths and stuff like that. And you still get a better prediction. It's also interpretable, which we will play with. And I think it's like it's something where future research could get a lot of nice ideas. So once it could serve as a baseline for the better GNNs, or you can also like design new zero-cost proxies inspired by those graph features, because when you've got those path lengths and node degrees, it's like a bunch of features. It's not that many, like on Dart, it's, I think, a bit over 1,000. On the other search spaces, it's a bit less. But still, it would be really good to have a new proxy that you can just use the one score. And maybe this score would also then be applicable in some non-standard search spaces. So I will show that in the hands-on. Before we move to the hands-on, so that we have a quick break, when we were designing the tutorial, we had some weak moments because designing a tutorial is hard. So just before flying to Paris, I sent this to Jovita. But in the end, it wasn't that bad. It's actually good. We really enjoyed the conference. So I hope you enjoyed the conference too. And now, if there are some maybe questions on graph, but we will see that in the hands-on. Okay, there's a question there. Is there? Okay.
So I was just wondering, because this graph properties thing is only something that can exist in a graph-like search space, right?
Yes.
So if we move to more funky spaces, like, for instance, I don't know, something that looks kind of like OFA, for instance, where you have some embedded kernels, shouldn't it be better to have some zero-cost proxies that work in all the possible search spaces? Or is it something that we should strive for?
Yeah, that's an excellent question. So that's maybe the main disadvantage of graph, that it's very restricted to the search space that you have, and also maybe not that applicable to the macro or the chain structured search spaces. We also got like a variant of graph for transnaz bench macro. And it turns out that the predictors can't really work with the one-hot encoding, at least, for example, the random forest. So so an example, if you got the transformer search space and you would have the number of attention heads, if you represent that as a one-hot encoding, then somehow the predictor cannot learn the interpretation of that. Or if it would be like a number of operations, if then it somehow cannot sum it up. So just like really writing is at, I don't know, 64 attention heads or like 3 convolutions, this already helps. For the TNB macro, I also, so it's like different stages when you can increase the number of channels. And just like having features at one point that will take, there were 1 channel increase, 1 channel increase, 2 channel increases, 3 channel increases, just really interpreting it for the predictor helps. So I think there is a big potential in designing features like this. Sure, it's not this standard graph for the directed acyclic graph search spaces, but it's still something like promising, and it's also interpretable because it's no longer just some one-hot encoded feature that's important, but you know that the number of the attention head is important.
Do we have any other questions?
All right. Just a quick recap. So now we will, oh no, introduction to the hands-on, sorry. So we will look at the graph library. Basically, it's refactored code from the ICML publication. So it now should be easily usable for your projects, your search spaces, and also for easy computation of zero-cost proxies. It's basically a wrapper around NASLib, but it should be really easy to just connect it to your code. But it also means that you can use all the features of NASLib. I will also show you how we did the interpretability analysis by Shipley values. And yeah, there, I included a few of exercises, so you can either watch me describe the notebook, or you can also like play with it. I put the link apart from the QR code into the Discord channel, AUTOML24 general channel. All right. So you got the Colab notebook. So if you want to save your edits, just save it to your drive in the menu. There's the installation. You ran it here, right? No, you didn't. Okay, then I will simulate that. So there's the installation of the necessary packages. After you install it, restart the runtime. Otherwise, it will not work. So after these two cells run, then restart it again. I will let it running and just talk about what's already written there. So I will show it for NAS-bench 2.1 and CIFAR-10, but there's other search spaces the same as in NAS-bench suite 0. So it's like 301, 101, also maybe trans-NAS-bench, and a lot of data sets. You can check that out because the NAS-bench suite 0 data is like a bunch of JSONs that you can download. All right. We'll see when it computes. So basically in Graph, you can compute the zero-cost proxies that are included in NASLib. You can compute the graph features I talked about, and you can also easily do performance prediction. And you can also include new zero-cost proxies or graph features. I try to make it as user-friendly as possible. I hope I succeeded. So first, how you represent the search spaces. So for example, NAS-bench 2.1, since it has 6 edges, it's represented like by 6 numbers. It's the same as in NASLib. So for example, in here, the interpretation, you can directly get it from Graph. So you initialize a NAS-bench 2.1 object, you get the network hash to it. And when you print the network, it's just a hash. But you can call to Graph, and it will convert into a graph representation where you get the edges. So the edges is always 2 nodes connected and the operation value at the specific node. And you've also got the interpretation of the operations. So for example, now you see that 0 is skip connection and 2 is 3x3 convolution. So it's basically just a straight chain of convolution, and elsewhere you've got the skip connections. How much time do we have anyway? Okay, there's still a lot of time. What you can also do is that you can directly get the model. So PyTorch runnable model. So it's in fact like a NAS-bench object that was like parsed into a model, but you could, if you want to use anything else, you will just make a class that inherits from this MB201 object and implement your own translation into the PyTorch model. As you can see, it actually works. I think it's a good, yeah. Okay, seems like it's successfully installed, so we will restart it. Okay, and now we should be able to run everything. Yeah, seems like it works. Yeah, it works because if it takes a long time, it works. It's importing all the packages. Okay. What I also, so in NASLib, you can iterate over all the networks in a search space. So I just put like a function that calls that. You have to download a NASLib dataset API. So there's a function for that. We downloaded the dataset APIs at the top cells. So now if we just look at it, we get an iterator that would just generate all the possible combinations of the 6 numbers here. All right, so just you can really quickly get all the networks from the NB201 or some other search space. Then there's the zero-cost proxies. So you can just easily, so first for the zero-cost proxies, you need some data loader because a lot of them are data dependent. So here I computed SimFlow. It first downloaded CIFAR-10. So I used just, this is like using the NASLib data loader for zero-cost proxies. So there's a configuration for that. So just do the same when you use it. Or you can also like make your own CIFAR-10 data loader. It doesn't really matter. And as you can see, it just computed the SimFlow score for the network that we had on the top, the chain of the convolutions. Super easy to use. Finally, the graph features. So I always represent them in config files. There's also some objects that you can use, but the config file basically describes everything that should be computed for a network. So it's like operation count. There's the minimum path length, and it internally computes all the combinations of this operation list. So it will generate skip, none, etc. Then both skip and none, both skip and convolution 3x3. So it's kind of a combinatorial explosion. If there is too many operations, there would maybe be a potential for feature selection, but we had some experiments. It didn't work that well. So that's still an open research question. But usually the search spaces don't have that many operations either, so it's not. It's usually not a problem. Anyway, this will then, when you load the JSON, enable you to load the features from the configuration file. So you see that the features that you loaded, or I will also print maybe the number of features that we have. Features, okay. Oh, len. Yes. Len. Right. So we got 94 features here. And when I look at two of them, it's just some feature object and constraint feature. Constraint feature means that you go just only over some of those operations. And here you can see that they have like names. So it's like operation count, minimum path length when you go only over those two types. Yes. And when you have the search space objects from before, if you get the graph, like the edges and operators, and pass that to some feature, you can just directly compute it. So here it's like you restrict yourself from the skip connections, and the result is 1 for minimum path length. And that's because there's a connection from the first node to the fourth node. So first node is the output, fourth node is the input, output. Now the fun part. This is how I came up with the graph features, or how we really got them working, because we look at NASPOT and we saw things. You will saw things as well. So when you load all the networks in NAS Suite 0 for MB201 and the zero-cost proxy scores, I included a nice utility function so that you can actually get them in a data frame instead of JSON. So yeah, one side note, MB201 is a little bit weird. You can check out our paper for more details, but basically there's some dead branches because zero operations don't allow some convolutions to go to the output. So we just remove them because they cause the zero-cost proxy scores to be a little bit weird. So instead of like 15,000 networks from MB201, we get down to 9,000. I could talk about this issue a long time if anybody is interested, because it was kind of annoying to deal with it during evaluation. Anyway, the nice data frame has like, again, the encoding of the network, validation accuracy, and then all the zero-cost proxies in a neat format you can use. All right, now let's go to plotting. Let's go to scatter plots. So NASPOT, I think it's the best proxy on MB201 and many other search spaces. You look at it, there's like some weird clusters, right? So what I did when I was designing it, I just look at the top networks or at the bottom networks, and I was looking at the numbers and interpreting the edges. I was like, what's going on here? And then I started noticing that they start looking similar. And actually, I discussed that with Arjun, and he was like, hey, maybe just look at the operations that are there. Like, if there are similar operations, then maybe look if we can somehow analyze that. I did that. So I, oh, okay, I didn't do something here. Wait. So I plotted it again, but I set the hue to the number of convolutions. So here you can see how using the features that we had, I can just evaluate operation counts for all the networks in the search space and sum the number of convolutions by 1, and 3 by 3. So basically NASWOT is just fancy number of convolutions. Only on MB201. On darts, it seems to work fine. But it's good to know that if the search space is fairly simple, you should really look into this. So some of the clusters are still a bit fluffy, but if you look into the number of convolutions 1 by 1 and 3 by 3 in these clusters, it's actually subdivided. So the top part is the 3 by 3, also some noise, and the bottom part is 1 by 1. So an optional exercise for you, if you want to get familiar with the API of this library, you can try to just analyze it again, like look at one of the clusters and again have the hues and just look at the number of convolutions 3 by 3 and verify if I'm not lying to you. Yeah. Another exercise, if you want to get familiar with that, is to look at other search spaces. It's the same. You have to just set the correct things at the top where the global variables are set at the top of the notebook. Get the correct JSON from MB-Suite0, and yeah. Now the thing that might be interesting to you if you have a search space and want to do performance prediction there. So how do you get a nice data set for performance prediction? So it's something that you can do here. So that's what the graph object is for. So you get a benchmark, you get a set of features, which is either a list or a config file. You got zero-cost proxy names or maybe zero-cost proxy objects, both is possible. You can also implement some caching so that you don't compute the zero-cost proxies on the go, but you can also compute the zero-cost proxies during creating the data set. And yeah, there is some caching implemented. So this enables you to just compute all the features for a given network and either retrieve the cached ones or compute the zero-cost proxy score for the network. It was fast, so it used MB-Suite0 data. And if you use this, which will then run for some time, so I will I don't know, 30 seconds or something, it will create a neat data frame for, well, for every of the networks, you get those features and also the zero-cost proxies. So once you have that, you can directly start with performance prediction. Yeah, once we got the data frame, you could also analyze it like before. So maybe you could look at correlations of the individual features, look at which one of those are correlated. I didn't do that yet. So maybe some of those features are actually really good proxies. So it could be interesting to do. Once we have it, which I don't know if you have it yet. Yeah, we don't have it yet. So I will keep on talking. We can train a performance predictor. So since it's just a table, a data set, we will just get the splits and we will just put it into a random forest and evaluate it. So that's what I did here. And so the train, it's just 100 networks you evaluate on the rest of the search space. And I know I said that we maybe shouldn't use just Kadlecová or just correlation. Nevertheless, we get the metrics here. We see that the correlation is quite high. Yeah, if we had more time, I could also then plot how it looks like predicted to validation accuracy. It's compared to the zero-cost proxies, it's just a neat prediction. So that's also nice. Yeah, also ideally do it over multiple seats, average, good scientific practice, right? All right, So this is performance prediction. And as you can see, it's just a setup in 3 cells. So once you've got all the, if you implement your search space in this, it's really simple to set it up. Then you can also do interpretability. So since the predictor is a simple random forest, you can just use, for example, a tree explainer from SHAP. And this gives you the importances for the individual features. So for one feature or zero-cost proxy, you get one Shapley value. And if you then sort by the most important features according to that, you see what is important for CIFAR-10 performance prediction. So it is, in fact, the zero-cost proxies. So I don't say that the graph features are better than zero-cost proxies. In some sense, they have some advantages, but the zero-cost proxies are like an aggregation of the properties. So if we can aggregate the properties of the graph, it really helps us. That's the same also for the macro search spaces. If we get a zero-cost proxy that describes some properties that are beneficial to the given task, it's really good for it. But it's not only the zero-cost proxies. Also, node degree here is important, and this one basically says how I interpret it. If I think this is the output nodes, yeah. So if there is like a lot of skip connections or average pooling going out to the output node, it's maybe not leaving the information from the convolutions through because it's either pooled or not really connected. So you can get some idea. The interpretability was really nice when we look at that other data sets. So for example, for the autoencoder task, the number of convolution or NASVOD were not important at all. Instead, I think the minimum path length of skip connections was really important. This was also something that some related work showed us. So we could really see, maybe that's also an answer to the question before. Using this, we can maybe see what is important for a given task, what property. And it would probably be hard to do, but if we could then scale up and like design big networks with a lot of skip connection, if the tasks like it, that would be kind of cool. All right, I will probably not run it so that I don't break anything in the input. Now, also there are some exercises. Again, you can look at it. I will not talk about that so that we still have some time for questions. Extensions. So you can have it as an exercise, or you can just a quick idea how you would implement something else. So for example, a new zero-cost proxy. What you would do here is that you would have a function that accepts the network, like the PyTorch model, and you want to compute the parameters just from convolution 3 by 3, not the whole network. So here, if it's like a convolution and the kernel size is this, then you will sum up the parameters here and return that. Just for reference, if I then use the function that I just defined as their zero-cost proxy, I can see that for the first function, the number of convolution here is slightly lower than the number of parameters overall. So I guess I hope it works. Then you can also, here's just how you would register that so that it works with the configuration with the graph object for the whole data set. The next part is introducing like a new feature. It's again similar, you just define the function, you get the graph, and here it's a ratio of convolution 3 by 3 to 1 by 1. So basically you just look at if the operation is 3 by 3, you will count it. If 1 by 1, you'll count it, and then you will return the ratio. And when you look at it, so for this network, the ratio is 1 because there's the same number of convolutions 3 by 3, 1 by 1. Here there's a 1 by 1 less. And again, if you register it to a feature dictionary here, or you could just change the code, like fork it and make some changes, you can then use it via the configuration files. And again, lots of ideas you could design tons of graph features. Like, for example, one idea is the number of bridges. Like, is there an operation that if you remove it, then the prediction just breaks? So especially for maybe the largest search spaces, that would be like an interesting feature to compute. Lastly, this is probably interesting for you if you have your own weird search space and want to use zero-cost proxies or features for that. So basically, you have to implement a bunch of networks. You have to get the graph. So it's the operation names to IDs map and the edges. Or, yeah, so you can then design your own features and your own graph. There's not a problem. You can also get the one-hot encoding because you can also compute it in graph, and you can you also want to create the PyTorch module. So this is important. If you want to compute the zero-cost proxies, you have to have this function here. And these are just utility functions to enumerate all the networks in the search space, and also again the operation map, but the other way around. So IDs to the names. All right, so we still have some time for questions. So if you find this work interesting, or if you think you could use it in your own research, try the exercises, or you can also contact me and let me know if you have any questions now.